For today's lesson, you'll want to pull out or be looking at the lesson 8.3 guided notes. I want to talk through a few problems in these guided notes, beginning with number 11 and then going into some area of composite figures problems as well. So number 11 asks us to find the area of this shape in square kilometers. We can notice that this figure is a trapezoid. However, all of the measurements are given to us in meters, but there is a scale given off to the left that 1 meter represents 5 kilometers. So I very strongly suggest that you start off by converting each of these dimensions from meters into kilometers first. And we'll delete that. Oop. Bear with me for just a moment. There we go. So our 1.6 meters is equal to 8 kilometers. And I get that by taking 1.6 and multiplying it by 5 to get 8 kilometers. Our 1.8 meters on this left-hand side times 5 is going to get us 9 kilometers. The bottom, which is 4 meters, multiply that by 5 to get 20 kilometers. Our height is actually the same as the top. And then the right-hand side is 2 meters, multiply that by 5 to get 10 kilometers. So what we did here is we converted each of the measurements in meters to kilometers. And the reason why we do this first is because even though 1 meter is equivalent to 5 kilometers, it doesn't mean that 1 square meter equals 5 square kilometers. So we can't just multiply our answer that we get by working through the problem with meters by 5 at the end. It's not going to work. However, if you multiply or convert each of the units at the beginning, multiply each of them by 5, we don't have to do any of that extra work at the end. So you can see the work here off to the right-hand side. The formula for the area of a trapezoid is half times the height, and then in parentheses, b sub 1 plus b sub 2. For this problem, I am not going to use, I'll cross these out, I'm not going to use the 1.8 meters or the 2 meters. So I actually don't need to use this measurement at all or this measurement. The reason why I don't need to use those is because the h, the height, is the 1.6 meters, this guy right here. So we'll replace h with 8. And then the b sub 1 and b sub 2 are the lengths of the parallel sides. So 1.6 and 4, which again are 8 kilometers and 20 kilometers. So we're going to do half times 8 and then in parentheses 28. 20 plus 8 is 28. 8 times 28 is 224. Multiply that by 1/2 to get 112 kilometers squared. Again, if you do this problem by using the measurements for meters and try to multiply by 5 at the end, you can certainly try it. You are not going to get 112 kilometers squared. So just be aware of that. There are a couple of questions on the area of composite figures and of the shaded region additional practice sheet, including numbers 4 and 5. So it may not be a bad idea for you to try those after watching this video. Feel free to pause it now and complete them at this point if you want. All right, let's talk a little bit about composite figures. So composite figures are something that are seen a lot of times in real life. You'll notice we have a couple of outside porches that aren't necessarily perfect rectangles, or there are multiple rectangles put together. You notice when we look at sort of a view of different rooms in a house, which kind of feels like we're trapped in our houses right now. But you'll notice that all of these rooms aren't necessarily perfectly rectangular. There may be cutouts for doorways, for windows, for closets and things like that. We have this pool down here. It'll be nice once the weather's a little warmer, we can get outside. It's not a perfect circle. It's not a perfect oval. So we consider those composite figures. They're made up of more than one simple shape. So when we talk about what composite figures are, these are shapes that are made up of more than one simple shape. And again, most shapes in real life are composed of more than one simple shape. I would encourage you when you're getting outside over the next week, when you're walking around your house, when you're watching TV, try to identify some composite shapes or composite figures. To find the area of a composite figure, you want to split or break it apart into figures that you do know. And there's multiple ways to do this in most problems. Find the area of each shape and then add the areas together. Sometimes you may have to find a missing side length that's not directly given in the problem, Please make sure you do not guess what the side lengths are. Don't say, well, I think that looks like it's 5 meters. Looks like it's half of that other measurement or length. We don't want to assume anything because it's not always perfectly drawn to scale. We'll talk about how to do this, but make sure you're using math to identify each of the missing side lengths. So let's go into our examples. We're going to begin with question number 12. This kind of looks like an ice cream cone, the way it's sideways ice cream cone. We can split it into a half circle here on the left-hand side and then a triangle on the right. So the first thing we're going to do is we're going to find the area of the semicircle or half circle. So I did actually draw a picture of what this shape looks like down below. You don't necessarily need to do that, but it does help us to identify the key parts. So let's remember this is a semicircle. The formula for the area of a semicircle is half times pi times the radius squared. I know that the diameter of this semicircle is 9 because it goes the entire way across the circle. That means the radius is half of that, which is 4.5. So we'll do half times pi times 4.5 squared. Now I'm going to go through the work really quickly. If at any time you feel like you want to pause the video to practice plugging this into your calculator, please feel free to do so. 4.5 to the second power is 20.25. Take half times pi times 20.25 to get 10.125 pi, which is about 31.8 yards squared. Again, that's for just our semicircle. Don't forget the 1/2 in the formula. It's very easy to forget that. I know I've done it before. Students do it pretty frequently. Since it's a half circle, don't forget that 1/2. Now, we also have a triangle as well. So this triangle, we are given, I kind of drew it down below here. I put the height inside the triangle, although it's given outside the triangle up here. The height of this triangle is clearly 13 yards. The base of it's not labeled, but it also is the diameter of the half circle. So it's going to be 9 yards. So you're going to notice that I jotted that down there. So this guy right here is going to represent the base of our triangle. The formula for the area of a triangle is half times base times height. So we'll do half times 9 times 13. That's going to get us 58.5 yards squared. And again, that's for the triangle. When we go to find the total area, what we want to do is we want to add those answers together. So our approximate 31.8 to our 58.5 is going to get us about 90.3 yards squared. And I didn't put approximately equal to, but the 31.8 is rounded, but it's going to get us about 90.3 square yards or yards squared. All right, let's take a look at number 13. So you're going to notice in number 13 that I broke this down perhaps a little differently than you may choose to break it down. I did include a box down at the bottom. Is there another way to break this figure apart? You may want to take a moment and think about how you could have broken this apart differently. So I broke this down into 3 different regions. So I'm going to start with one of our rectangles, and I drew these horizontal lines in here. But I'm going to make this region 1 right here. So that's going to be this guy. Our dimensions are 8 by 3. And for a rectangle, we take length times width. So the area is 8 times 3 or 24 miles squared. Again, that's for region 1. I'm actually going to go down to region 3, which I'm going to call this guy right here in blue. And that's going to be this rectangle down here. So the dimensions of this are 6 by 2. So I'm going to take 6 times 2 to get 12 miles squared. Now the hardest one to figure out is this one that's in the middle. I'm going to highlight it in green. So that's going to be this guy. And that's also going to be this work down here. So we'll try to color code this to make it as easy as possible. You're going to notice that I filled in these boxes. This length across is 4 miles. This length going down is 5 miles. So in order to figure this out, what we need to recognize is that this entire length across here is 8, as shown up here. This part is 4, which means this other part needs to also be 4, since 4 plus 4 is 8. Then going down, this entire length is 10. This part is 3. This part is 2. 3 plus 2 is 5. That leaves me 5 miles for this length. So you're going to notice I jotted those down here. The area is 4 times 5, which gets us 20 miles squared. Add 20 to 12 to 24 to get a total area of 56 miles squared. Now, hopefully you've taken a moment to think about another way you could have broken this down. Instead of making horizontal lines, you could have drawn vertical lines in here. So I could have broken it down here and then here as well. So the in-between steps and the work in between might look a little different, but you should get the same final answer. You could even draw a vertical line and then a horizontal line. Just make sure you're able to calculate or find any of the missing side lengths you need to find the areas of those rectangles. And this looks a lot like what a floor plan on a house might look like too. So this is a really good real life kind of situation. All right, let's go ahead to number 14. So number 14, I would suggest breaking this guy down into a half circle and a triangle. Let me actually move this down just a little bit. There we go. So break it into a half circle, and I said a triangle, but technically we have two triangles here. They happen to be the same size though, so we'll talk a little bit about that. So let's go ahead and, oops, bear with me. Let's go ahead and delete this. For the semicircle, we need to recognize that the diameter is 20 since it goes the entire way across this thing. Half of that is 10, so the radius is 10. So since it's a semicircle, we do half times pi times the radius squared. Again, the radius is 10. 10 squared is 100. 100 times a half is 50 pi. So for this semicircle, we get about 157.1 meters squared. Now for the two triangles, we can actually treat those together since they both happen to be the same size. They both have the same base and height. The base is actually the radius of the semicircle, which is 10, and then the height is 8. So we can do half times 10 times 8 for each triangle. That's going to get us 40, and again, that's for each triangle. But I doubled that since we have two triangles to get a total of 80 meters squared for the two triangles together. You could also do 40 plus 40. You could do them separately. Some students might even realize that you could take the 1/2 out of the formula and just do base times height would also get you 80 meters squared. We'll now add those guys together to get our total area. And again, you may need to pause the video to jot some things down at some point, and that's okay. Add 157.1 to 80, and you should get 237.1 meters squared. All right, so question number 15. We have a rectangle and then two semicircles on either side. Let's begin by taking a look at the rectangle in the middle. The dimensions are 16 and 11, so we'll do 16 times 11 to get a total area of 176 inches squared. The two semicircles, if we put them together, form a whole circle. So I'm going to find the area of one semicircle and then double it. So the diameter of each of these semicircles is going to be 11 inches, which means the radius is half of that, 5.5. So do half times pi times 5.5 squared, and each semicircle is going to get us an area of 47.5. Double that since we have two of them. You could also take the 1/2 out of the formula. That's going to get us 95 inches squared for your two semicircles, which again form a whole circle. So to find the total area, we want to add the area of the rectangle to the area, whoops, we'll leave that guy there. Area of the rectangle to the area of the two semicircles together to get a total area of about 271 inches squared. Okay, number 16 we're going to do together, and then I would suggest maybe taking a look at 17, 18, and 19 on your own. I will put the work up here so you can see each of those and just talk about the highlights of each of those problems, because I know this video can get quite long if we walk through every single problem. But I do want to give you a chance to try some on your own before you go into the independent practice on this. So let me get rid of some of this work here. So this shape, or this box here, I should say, this shape consists of a rectangle and then two triangles that are the exact same size. So let's begin with the rectangle, which is on the right-hand side here. The dimensions are 24 and 8. 24 times 8 is going to get us an area of 192 yards squared. And again, that's for our rectangle. Then we have two triangles. They're the same size. Now, a lot of times I have students who see this dotted line in here and think they need to split this big triangle into two little triangles. You don't need to do that. That's the height of this big triangle that I'm going to outline right here. So the formula for the area of one triangle is half times base times height. The base and height are going to be 24 and 8. So we do half times 24 times 8, which is going to get us 96 for each triangle. But we have two of them. So we're going to take 96 times 2 to get 192 yards squared for the two triangles together. Now, let's add those numbers together. There we go. Add those numbers together, the 192 for the two triangles, the 192 for the rectangle, you get a total area of 384 yards squared. All right, so numbers 17, 18, and 19, you may want to pause the video at this point and give those a try. We've seen problems relatively similar to those. What I'll do is you can pause the video, we'll get restarted in just a moment, and then we'll just kind of quickly go through the work for these. All right, so hopefully you've given these problems a try and didn't find them too difficult. In fact, number 17 is pretty similar to the first one we saw. This is composed of a triangle and then a semicircle. Now, again, a lot of times students try to split this big triangle into two little triangles. No need to do that. Base and height are 10 and 15. Total area for the triangle should be 75. And then we've got the semicircle with a radius of 5. Half times pi times 5 squared should get you about 39.3 centimeters squared for that half circle or semicircle. Add those answers together to get about 114.3 centimeters squared. Feel free to pause the video at any point so that you can check your answer, check your work, or correct anything. All right, moving on to number 18. I will point out number 19 is a really tough one. So if you didn't get number 19, please don't panic. But for question number 18, this is composed of a rectangle and a triangle. The rectangle has dimensions 10 and 5, so the area will be 50. The big triangle that we have up here has a base of 10, height of 3. Half times 10 times 3 gets us an area of 15 centimeters squared. For a total area, we want to add 50 to 15. That should get us 65 centimeters squared. Again, feel free to pause the video at this point and correct or jot down that work. In the meantime, I'll delete these boxes here. Let's take a look at the last independent practice problem on this. And this is a really tough one. So if you did not get this one, don't panic. I suggest drawing an extra line in here, and I'll go ahead and construct that right along here. That's going to be the other side of our rectangle. So let's begin with the rectangle. It has dimensions 9 by 6. 9 times 6 is 54 yards squared. We also have a triangle over here. The height of this triangle is actually the 5 yards. I'll highlight it in yellow. That's this guy. It's outside of the triangle, but it's the same as this length right here. And then the base, of course, is 6. So half times 6 times 5 gets you an area of 15 yards squared for that triangle. We have two semicircles. We'll begin with the larger semicircle here. It's got a diameter of 9 and a radius of 4.5. That's not an approximately equal to it, just got a little blurry there. Half times pi times 4.5 squared is going to get us about 31.8 yards squared for the bigger semicircle. The smaller semicircle is 6 yards, which now looks like it could be pointing to this guy as well, but it's actually really this diameter of the smaller semicircle. So that means the radius of the smaller semicircle is 3. Half times pi times 3 squared is going to get us about 14.1 yards squared. Down below, we add all these together, the 54 to the 15 to the 31.8 to the 14.1. We should get about 114.9 yards squared. All right, again, I want to point out that on the area of composite figures, and of the shaded region additional practice, there are some really good problems with this. Number 6 and 7 are very good ones for you to try. I also want to take a look at one last problem. Numbers 20 and 21 go together. And I want to talk about how to treat something like this. On the test that we have for this unit, there's a problem just like number 20. Now, I don't think we'll ever end up taking that test, but I do like to talk about this problem. So there's a lot of ways you can split this up. I've seen students break it down. I'll delete this in a moment, but break it down actually into a trapezoid here and then make this one big trapezoid, or a trapezoid, trapezoid, and triangle. I've seen students do that. More students are probably going to break it down where they make a vertical line here and form rectangle, rectangle, and then a triangle. You could also split it along here, drawing a horizontal line. So there's more than one way to do this. And, if you have lots of time on your hand, feel free to maybe try it on your own. You certainly could do that, but using a different method. So let's start off with this rectangle on the left. I'm going to highlight this. This is going to be region 1 right here. So our dimensions are 9 by 4, which is going to get us an area of 36 feet squared for this region. Now we have a rectangle in the middle as well. I'll highlight that guy in green. And I'll highlight the answer in green too. Sorry, I should have done that for the previous one. So let me highlight this guy. So for the rectangle in the middle, this is kind of tricky for students. This length right here is 9. But this length is not 4. Sometimes students think, oh, well, that's 4. That means that has to be 4. Well, this entire length is 9. So if this part is 4, then the rest of it needs to be 5. So we need to take 9 times 5 here to get us 45 feet squared. Now our last region is going to be a triangle. The area of that guy is going to be 7.5 feet squared. So I do half times base times height. This dotted line right here is also 5, like the other side of the rectangle was. For the bottom, we need to realize that this entire length is 16. This part is 4. This part is 9 for a total of 13. That leaves us 3 for this length. So if we do half times 3 times 5, we should get an area of 7.5 feet squared. Now you technically can include this green and blue region as one big trapezoid if you want, with the height being 5. That is another option. This is, again, a really perfect example where you don't want to just guess what you think the length is. It's not drawn to scale. I created the picture, so it's certainly not perfect. You also may realize that you didn't need this 5.8 feet for the height or base of the triangle to find the area of it. That will actually be needed for problem number 21 in just a moment. Now, the question that is on your additional practice sheet actually has you converting the measurements first from inches to feet using a scale. So it's a little more challenging, and then finding the area. But it's really the same figure, just with different numbers in the picture. Total area here, add your 36 to your 45 to your 7.5 to get a total area of 88.5 feet squared. Now, when we go to look at number 21, it says find the perimeter of the figure in number 20. The perimeter is the total distance around, so all we need to do is add all of the outside measurements. You don't need to use 2L plus 2W for the rectangles because I'm not including this segment, for example. I just want to find the total distance around the outside. So what I want to do is I want to add together 4 plus 4 plus 9 plus 5.8 plus 16 plus 9. That's going to get us a total perimeter of 47.8 feet. Now again, I know this was a long video. There's a lot in here, so you may need to pause it. You may need to rewatch some of the parts. This is an important concept because it is something used in real life. It is something that combines some of the skills we've already done with area of simple figures. But you do want to try some extra practice on this. So like I said, from here, you may want to go to area of composite figures and of the shaded region additional practice and complete numbers 4 and 5, which are not composite figures. They're just using scale. And then number 6 and 7, which are composite figures, along with number 8, which is very similar to problem number 20 and 21.